Okay, let's regroup. Where's Gabriella? Gabriella Mungia. Tell me about a P sequence and P series. When do each of those converge? She wants the P sequence converges when P is greater than 0. Yeah, the sequence, all you need is a positive P. All you need is a positive P, and the denominator will get large, and then the whole sequence will converge to what? Zero, right? Okay, what about a P series? When does it converge? Okay, so P is greater than 1. So you need, for series to converge, you need that P to be larger than just the sequence converging, right? Okay, so what about geometric sequence and series? Where's Philip Perez? Philip, you here? Yeah. Tell me about a geometric series. When does it converge? Don't remember? Oh, right next to him. Yep. You don't remember? Okay. These are basics, guys. These are basics. Where is Alyssa? Sola? Yeah. Yeah, so when the value of r is between -1 and 1, or like a fraction, right? Because the idea of a geometric sequence is repeated what? Repeated multiplication. We keep multiplying by r to get the next term in the sequence or series. Okay? So the sequence converges when r is between -1 and 1. What about the series? When does it converge? Same. As long as the sequence converges, for geometric sequence, the series also converges. All right, how can you quickly conclude that a series diverges? Where's Benjamin Weinstock?
Oh, here.
Yeah.
So you can conclude that the series diverges if the sequence is not to 0.
Right. If the sequence doesn't go to 0, this is game over, right? If that sequence doesn't go to 0, it's got to go to 0 for the series to converge. So that's the first answer to number 5. Sequence must go to 0. If it doesn't go to 0, series diverges. End of story. Okay? If the sequence does converge to 0, then what about the series? Does it converge? Was it?
It might converge.
Right. Some series converge if the sequence goes to 0. Other series, if the sequence goes to 0, they don't converge. So that's the whole reason we're spending 2 weeks on this, is those series where the sequence converges to 0. Now, will the series converge or not? That's kind of the whole ball of wax here, okay? Now, if I have an infinite series that converges, how can we get an idea of its sum? Where is Jason Alexander? Jason Alexander. Different Jason. All right, what about Tristan?
Yes. You can tell if it converges, you can get an idea of what the sum is by taking the sequence of partial sums and going somewhat far into the sequence.
Okay, really any partial sum. Yeah, exactly right. But any partial sum is some kind of approximation for the series. Because what is the series? What is the series? It's just adding them all up, right? So if you add some of them up, it's going to be an approximation. Does it make sense? Right, the series is adding all of them up. So a partial sum is just adding some of them up, and a finite sum. So any partial sum becomes an approximation for the series. And then how do we get the exact sum, Tristan? Right, now make the sequence of partial sums, and each term in the sequence has one more term added on. If you take the limit of that, well, that's going to be the value of the whole series, adding them all together. So the limit of the partial sums. Sequence of partial sums. Okay, any questions on this warm-up? Now that our minds are back oriented to these basics, we can advance the conversation. Any questions? Any questions? Yes, please.
Could we also answer number 6 with a over 1 minus r, or is that g?
Only if what?
Geometric.
Yeah, only if it's geometric. That's the only one we have like a formula for, is the geometric series. Yep, a over 1 minus r. Other questions, comments? Okay, so let's see here. So we want to talk about something today called alternating series. Alternating series, they alternate between positive and negative values. Make sure you're thinking and listening, not just copying down word for word. You can always take notes in the video later. So alternating series, the terms alternate between positive and negative, and so we can always express that like this. Remember, -1 to the I makes our terms alternate. And so then BI would be like all those terms if they were the positive versions, right? So the sequence BI has all positive terms, and then you throw this factor on there, and that makes them alternate between positive and negative, and that's what we mean by an alternating series. Okay? So I want you to write the alternating harmonic series. Write the alternating harmonic series, use sigma notation, and express it in the easiest possible way. And do it so that the first term is positive. Do it so that the first term is positive. So I want you to write out with both sigma notation and its meaning in the simplest possible terms, the alternating harmonic series. And make sure. Where's Christopher Tithoff? Christopher here? Christopher Tithoff. How about Patrick Taylor? Patrick here? Patrick. How'd you do on this? Were you able to? So take your pick. You could write it, tell me sigma notation or just what it'll be as its meaning, like in the simplest possible terms. Sigma? Okay. He's offered up this as the alternating harmonic series. What do you think? Got a thumbs up, a yes, some nods, good, okay. So you could also have I plus 1, or you could also write what? I minus 1, just as long as when I is odd, you're gonna make the exponent even. Both of those do that, right? So I being odd makes the exponent even in both cases. And so then that first term is, so then what does this equal? Somebody new. Where's Devin? Devin, you. Yeah, Devin. So what is that? You see this and you think what? When you write, we see this, you think what? Uh-huh. 1 over 1, okay. This is I equals 2, right? So we're going to add these together? Okay. So 1 minus a half plus a third minus a fourth plus a fifth. Agree? That's it. Yeah, and you can have I minus 1 or I plus 1. I have I minus 1, but they both work. Okay, so this is the alternate harmonic series. And the harmonic series that didn't alternate, did that converge or diverge? Because the harmonic series is? What kind of series is that? Geometric? It's a P series, right? It's a P series with P equal to 1. That's the harmonic series. And so because p is not greater than 1, it diverges. But we showed it, right? We showed you could keep adding 1/2. You keep taking more terms and getting like sums, like partial sums inside that were always greater than 1/2, and then so that thing blew up and got really big. So we've shown that. And so what about the alternating harmonic series? So does it also diverge if the harmonic series diverges? What's this going to do, having every other term now subtracted? That's going to do in terms of convergence or divergence? Help the situation? Hurt the situation? Doesn't matter.
Don't all alternating series diverge?
No. But in terms of thinking about, adding up all the terms and it converging to a finite sum, does minusing every other term now, what will that do in the situation? Help? It's going to help, right? This is going to help because what we're worried about is adding up all these terms and it's getting infinitely large, right? So if every other term is subtracted, well, this is going to be really helpful towards the goal of getting this thing to sum up to a finite value, right? So let's do the sequence of partial sums. So what's the first? And we're going to sketch this visually. What's the first partial sum? 1. The first partial sum is 1. And so it's like we start from 0, the 0th partial sum, and then the first partial sum takes us to 1. So here we are at what? S1. The first partial sum. What's the second partial sum? Positive 1/2, right? We add together the first two terms. So what happens is, to get to the second partial sum, we're going to subtract 1/2, the second term. So that's S2. What's the third partial sum? 5/6. It's the sum of the first three. Something like that, somewhere in there. And then what's the fourth partial sum? Oh, you guys know your fractions. What is it? I didn't even know that. What is it? 7/12. A little bit more than 1/2. Somewhere in here. So what's happening here? Do you see that each partial sum is going to be somewhere between the last two? Do you see that? Every partial sum, S3 was between the partial sum of S1 and S2. S4, somewhere between S2 and S3. S5, similarly, between S3 and S4. So we're kind of, is this converging? It's going to converge on a value. Yeah, it's honing in on there's some value in here that this is going to collapse in on. So the straightforward harmonic series does not converge, it gets infinitely large, but when you make it alternate, you see this very helpful effect of subtracting every other term, and so then each partial sum is somewhere between the last two, and so we're going to converge somewhere in here, right? So this sum is going to converge somewhere in between, for sure, in between 5/6 and 7/12. But we could do much better, right? By taking more and more partial sums, we could get a much narrower window of where that thing's going to converge, right? And the bigger the partial sum, the better the approximation it is to the sum. So yes, this is going to converge. Okay, so we have something called the alternating series test. So an alternating series test, if you have a series like this, alternating, the first condition is, do the positive parts of the terms, is bi plus 1 less than or equal to bi? What is that in effect? What's that telling us about the sequence of positive terms? If bi plus 1 is less than or equal to bi, what is that in a nutshell or in a word? What is that talking about? The sequence does what? No, these are all positive terms. This has nothing to do with alternating. If bi plus 1 is less than or equal to bi. So what does that mean for the sequence? If the next term is less than or equal to the current term. Decreasing, right? The values are getting less. Okay, so the first requirement is decreasing. And then the limit of those is 0. The limit of the sequence is 0. So together, really our conditions are, is this positive part of all the positive terms, not having been made alternating, do they decrease to 0? That's what we're saying. Decreasing and getting infinitely close to 0, converging to 0. If you have both those things and it's an alternating series, then the series converges. Okay? Then the series converges. So remember when we were talking about the divergence test? We said, what did we say? We said, if the sequence converges to 0, does the series converge? Before we said, does it converge or not? If the sequence converges to 0. Sometimes, right? This was the whole maybe situation. Sometimes it does, sometimes it doesn't. Okay? Well we if the sequence converges to 0 and it's alternating, it converges. So now we can say that it converges if we have a sequence that converges to 0 and it's alternating. So put the alternating effect on any sequence that converges to 0 and the series will converge. Does it make sense? If it's not alternating, the jury is out if the sequence goes to 0. But if it is alternating and the sequence goes to 0, it converges. All right, so here's a couple of examples. Practice here. Here's two alternating series. So first of all, you have to decide if the alternating series test applies, meaning are these two conditions met? If these two conditions are met, then you can conclude it converges. Okay? Question?
Do these rules also apply if the first term is negative rather than positive?
You like -1 to the I?
Yeah.
Yeah, sure.
Oh.
Mm-hmm. Okay, so both of these alternating series are based on the natural log function, and so I'm going to show you, recall what the graph of natural log is. That can help. So this is our arguments for natural log, and the values of natural log would be graphed as the y-coordinate. So this graph might help to make heads or tails of these two. Okay, so see how you do on these two alternating series. So again, you're checking to see if these conditions are met, then you can conclude that it converges because it's an alternating series. If they're not met, then you need something else, right? If these conditions are not met, you need to apply something else that we've learned. Try these two examples, okay? Go. Anne-Marie here? How'd it go? Tell me about the first one. What's that? Yeah, what was your thinking through? So I kind of trying to guide you through the thinking here. So the ln, you're talking about ln of 1 over I? What happens to that as I gets really large? 0, infinity, negative infinity, negative infinity. 1 over I goes to 0, obviously, right? As I gets big. So what happens to natural log as we go to 0? This is going to 0 now. So natural log goes to negative infinity. Okay? So then what can we conclude about this first series? So this part right here goes to negative infinity as I gets big. What do we think? Converges? Diverges. By the alternating series test? What are the conditions for the alternating series test? Your sequence has to decrease to 0. Is that what this is? No. Alternating series test does not apply to this first one because this does not decrease to 0. That's what the conditions are for the alternating series test. The positive part of your terms has to decrease to 0. Is that what's happening here? No. These are doing what? Getting large, very, very large negative. Conclusion? The series diverges by? Why does it diverge? What do we have? What reason? Divergence test. Divergence test says what? If the sequence does not go to 0, game over. Remember, that's the first thing we always check for. If the sequence doesn't go to 0, the series can never converge. That was awesome. Okay? So it's the divergence test. It's just like we said, this is the very first test we check. If the sequence doesn't go to 0, end of story, game over, series can't converge. So this one diverges by the divergence test. How about this one? Converges. Why? ln of I goes to? ln of I, first of all, gets really big. This just keeps getting bigger and bigger. ln of I, so 1 over ln of I. This will decrease to 0. Therefore, converges by alternating series test. This one, the alternating series test applies because 1 over ln of I is a sequence that decreases to 0. Doesn't make sense. The first one diverges by the divergence test. The second one converges by alternating series test. Yeah, please.
How do we tell what it converges to these tests?
Okay, how can we find out what it converges to? So that's the question we've been asking. How can we get an idea and how can we know exactly? Remember? How can we get an idea what a sum converges to?
Just put in this.
A partial sum, right? A partial sum gives us an idea. And how can we get it exactly? Take the limit of the sequence of partial sums. Take the limit of the sequence of partial sums, and that will tell us what it converges to exactly. So add together, get the first 10 terms. The first 10 terms will give you some kind of idea of what this is going to sum up to. Take the first 100 terms. That's going to give you a better idea. Take the limit of all the partial sums, and that will be exactly what that sums up to. Partial sums help us to estimate the full sum. Other questions? All right, so there's something called absolute convergence. Absolute convergence. Here's the idea. The idea is, so we saw that alternating helps, right? Alternating the signs, positive minus, in terms of getting a finite sum, it really helps because half the terms are making it go back, right? Subtracting. So the idea of absolute convergence is, does a series require alternating help in order to converge? Or does the series converge whether it alternates or not? So here, the idea is, in a certain series, does it need that alternating help to converge? What's an example of that? What's an example of one that actually needs that alternating help in order to converge? Yeah. A harmonic, right? We saw that. So the harmonic diverges, but if you put the alternating signs on it, it converges. So that would be like exhibit A. Or does a series converge whether or not it's alternating Doesn't matter. It still will converge even if it's not alternating. Okay, so the second, case B there, we say the series converges absolutely. We say the series converges absolutely if it converges whether or not the terms alternate. Doesn't matter if the terms alternate. It'll still converge if they don't alternate. That's called absolute convergence. So mathematically, what would we say for mathematically? We're saying that if you take the negative signs off, right? If you take the alternating out and it still converges, then it converges absolutely. So a sequence converges absolutely if you took the absolute value of all the terms and added those up, it still converges, then your series converges absolutely. Does the idea make sense? Yeah.
I have a question about an alternating series that I don't really know if it converges or not.
Okay.
Like sine and cosine. I don't understand whether they.
Well, do the alternating series test. Values of sine. So if the y values of your points are like your sequence, is that what you're saying? Do the y values decrease to 0? Remember?
Yes, no.
Definitely no, right? They keep fluctuating between -1 and 1. So you don't have you need something that decreases. All the positive terms have to decrease to 0. So sine and cosine don't converge to 0. So it won't, even if you alternate it, it won't converge. Okay, so absolute convergence, the idea, does it make sense? Okay, if an alternating series will converge conditionally if the series converges, but not absolutely. So in the case A up there at the top, where the series does require alternating help to converge, we call that conditional convergence, or the series converges conditionally. What's the condition? That it alternates, right? It needs this condition of alternating in order to converge. So converges absolutely, that was this B. Converges conditionally, that was A. All right, examples. So the alternating and alternating P series. For what values of P does the series converge absolutely? For what values of P does the series converge conditionally? And for what values does it diverge? So here's a couple examples to help figure that out. So here's two alternating P series. So this first one, 1 over j to the 4th, alternating. Does it converge absolutely, converge conditionally, or diverge? What do we think? So we can test for absolute convergence by saying, take the alternating off, and just consider the 1 over j to the 4th. Does that converge? Does that converge? It does. Therefore, since so it doesn't need the alternating to help. Why? Because P is greater than 1. So since 1 over j to the 4th converges, P is greater than 1, the series converges absolutely. Does it make sense? That should make sense. whether it alternates or not, 1 over j to the 4th will converge. Therefore, this series converges absolutely. Okay, what about this one? What's p here? 1/3. So now, 1 over j to the 1/3. Converge or diverge? Diverges, because p is not greater than 1, right? But does this alternating series converge? How do you know? Because the sequence goes to 0, right? So p equals 1/3 means the series diverges, but 1 over j to the 1/3, what? But that sequence, 1 over j to the 1/3, that converges because p is greater than 0. And since that sequence converges to 0, and it's alternating, the series is alternating, it converges conditionally. Does it make sense? Any questions on that? All right, so this brings up something called, what about geometric series? Okay, geometric series. So what if r was between, so before we get to that example, if r is between 0 and 1, positive, then the geometric series will converge absolutely, right? Because it already converges. So it's not even alternating, but it's the terms are already all positive. If r is greater than 0, the terms are already all positive, so it's absolute convergence. So the real question with geometric series is when you have an r less than 0, right? Something like this. So this is the real question. And so does it converge absolutely? Conditionally? So we know it converges because we're between -1 and 0. But does it converge conditionally or absolutely? So what do? You test this. And what series do you get when you take the absolute value of all these terms? It's the same as if r was what? Positive 2/5, right? Which converges because r is between 0 and 1. Therefore, absolutely convergent. Converges absolutely. So taking a geometric series where r is -1, or r is negative, that makes an alternating series. Making all the terms positive just makes a series that converges with a positive r, less than 1. Therefore, the conclusion is all geometric series converge absolutely. Yeah. Yeah, and r is 2/5. No, so that was the trivial case. If r is greater than 0, we have absolute convergence, and that's just trivial. So now the real question is, when r is less than 0, do they converge or not? So that was really the real conversation is for an example like this. So we just showed all geometric series converge absolutely. Okay, so then there's this thing called the ratio test. Let's just talk briefly about the ratio test. We'll get too far into it. But we got to get the idea for the quiz today. We got the ratio test. So the ratio test says if you have an infinite series, you can evaluate this limit. So you make a new sequence taking the ratio of consecutive terms. So ai plus 1 is the next term after ai. So you make a ratio out of that, and then you make a sequence of those. And you take the limit of that sequence. So you analyze this sequence made of ratio of consecutive terms. And then you have these conclusions based on what that limit is. So let's see what this is about. Here's the important part. What was the deal with the geometric series? What's the idea of it? Repeated multiplication by this constant value r. To get the next term, you always multiply by r, the previous one by r. So let's take that same, look at that same idea and say, just in any series, right? So this is any series now, made of the sequence Cn, Ci. So for any series, what would you multiply by to get the next term of the series? So the question is, what do you multiply Cn by, so call it x, like you're solving an algebra problem, to get Cn plus 1? What would you multiply? If you're solving for x, you'd multiply by what? Cn plus 1 over Cn, right? Just doing the algebra. Just divide both sides by Cn. So the multiplier is C is the next term divided by the previous term. That's what you always multiply by to get the next term. So if you're at Cn, you multiply by Cn plus 1 over Cn to get Cn plus 1. Should make sense, right? So for instance, this would be what? This multiplier would be C4 over C3. Multiplied by C3 would give you the next term, C4. So what is this saying? This is saying, look at the limit of those ratios. C2 over C1, C3 over C2, C4 over C3, or in other words, Cn plus 1 over Cn. Look at the limit of those. If those ratios converge on a value that's less than 1, then what is happening with this series? The series then is becoming like what? If that ratio is converging to some value, then what's going on? It's like the series is becoming geometric, right? It's like becoming geometric with an r value of L. Does that make sense? And so then how would the series converge? If that limit of those multiplier ratios, what is like r would be less than 1, or between 1 and negative 1. So basically what the ratio test is doing is it's testing to see if your series is like becoming a geometric series that converges. Does that make sense? So it's testing to see if your series is becoming geometric by testing the multiplier and seeing if the limit of that is less than 1.